Okay. So we're looking at trying to understand why row operations don't introduce new solutions, why Gauss's method is safe. And this is a simple example of dealing with the row rescaling operation where I've taken one row and multiplied it by another row. And you can see that this doing one equation is the crucial thing, because if I had a long list of equations and a long list of equations here making up a linear system, the only difference between the two systems will be this equation going to this one. So that's where all the action is. And I could add more variables, but that would actually just make this look longer. It wouldn't actually change the core idea of what's going on. So if we can understand in this case what's going on, you can understand in the general case where things look more complicated, but they're not really more complicated. So we're trying to write down the definition of the set of solutions. There's a concept, the set of all values that make this equation true, where I substitute, like if I have a solution here, S, which is some specific values, S1 and S2. So these are constants, these are chosen values. So if I substitute these numbers, S1 and S2, for the variables X1 and S2, it should make a true equation. That's what we mean by a solution. And the whole solution set is written like this. Okay? It's the set of all the ordered pairs, X1 and X2, such that, that's the vertical bar, this equation is true. So in saying this, we're choosing particular values and deciding that. So how do I use this definition? Well, I'd say let's say we'll say that S, this S up here, is a member of S1. That's not a member of, that's equals. This is the membership symbol. This says this set of this ordered pair is a member of this set exactly when A S1 plus B S2 equals D. So I plug in, so A, B, and D are already numbers, and S1 and S2 are my chosen numbers. And so the question is, the values S are a member of the solution set if this is a true equation. Okay, that's what this means for this notation. It means I use this as my defining property of the solution set. Now, let's look at the same solution set for the second system over here. So this is, I'm going to need to take S2, but I need to write it down here for space reasons. Okay, so we're going to have S2 equals the set of all X1, X2, such that K, A, X1, that shouldn't be there, plus K, B, X2 equals KD. Okay, so what does, if I have some S that if I want to ask, is this also a solution of this set? Well, that's the question. Is S also a member of S2? Because these sets are the same if they have the same elements, if they have the same solution. So if they were the same, anytime I choose a pair that makes this true, it should be a member of this set. Well, to be a member of this set means, oh, I tested according to the defining property, S member of S2. This claim is true when K A S1 plus K B S2 equals K D. So if I wanted to compare these two sets,
Professor, is it supposed to be S1 and S2?
S1, S2, S1, S2, yes.
Okay,
So
just checking.
was the typography or something else?
Yeah, it was. I wasn't
This,
sure about what you written.
okay. The problem is this S here that looks sort of weird.
Yeah.
Okay, let me.
But I understand now. Thank you.
Okay. Well, it might be. I can. There. Okay. Okay, now the issue here is what makes this, how do I know this set's the same as this set? Well, one way is there's something in the in some of the climatization material that says, well, S1 equals S2, being the same solution set, is the same as saying, well, every element of S1 is an element of S2, and every element of S2 is an element of S1. And what this means is that if S is a member of S1, that implies, that's that implication symbol, S is a member of S2. And it has to go the other way around. S member of S2 implies that S is a member of S1. Because this first one says, well, if any element of S, if there's any element of this set, if these are going to be the same, it also has to be an element over here. This ensures that this first implication ensures that in going from S1 to S2, we don't lose any elements. All the elements in S1 are over here. The second one says, well, we don't have any new ones. If we have an element over here, it's also going to be in the original one. This first one says we don't lose any solutions. The second one says we don't pick up any solutions. Now, all four of these conditionals, all four of these membership terms are related to this being true and this being true. And what's going to turn out is that if this equation here is logically equivalent to this one, then these two sets will be the same, because if S is a member of S1, that means this is true. So what this says is that A S1 plus B S2 equals D implies that this is very long-winded. Because I'm trying to write things out in sort of detail that makes everything sort of explicit. And it may even then be hard. Okay, so this is this sort of 1 and 2, and this is 1, because what S member of S1 means is this is true, that the values S1 and 2 make the equation true, and that we need to know that if this equation is true, then this one is true. And the second one goes the other way. So it's like saying, I can put the arrow here. And this is what I mean by these two equations have to be logically equivalent. Now, are you following this? Does anyone have any questions?
Uh, I have a small question.
Okay.
The S1 and the S2, there's two different S's here. There's like a big S which
Yeah.
describes a solution set, and then
Yeah.
there's the variable S.
Yeah. So I'm trying to make the S lowercase. This this S here is supposed to be a lowercase s. So the S without the subscript, it's like the S without the subscript, the lowercase one is supposed to be, I know it's hard to read because you've got too many S's all over the place. Is that the problem?
Uh,
That you're,
Kind of. It's just that sometimes when you write it, the S's look similar in size even when they
yeah.
aren't.
Oh yeah, and then I have S1 and S2 over here. So this is like a notational thing. And so I guess it could look sort of like, how can we change this to simple, to make it,
Well, I understand it now. It's just that I needed
well,
to
I make
clarify
maybe
what was the little S and what was the big S, and
yeah, so I can see
figured that
how,
out.
and also I have here that S, since it's an ordered pair, I have little s1 and little s2, and so I have the big S. Yeah, so I can see probably if I was typing this, it would probably be less less involved. Okay, so hopefully, any other questions?
Someone wrote in the chat.
Oh yeah, I haven't got. Let me put that up. I keep forgetting to put the chat up. Nope, I don't want to do that yet. Let me bring this over. Oh, let me get this over here. Okay, good. Thanks. Okay. Okay, so someone said they're basically lost. So the question is, what can I say constructively? The idea here is we have a linear system composed of one equation, and we're doing a row operation where we multiply it by a number k that's not zero, and we'd like to know, did this change the solutions in any way? And the way we're expressing that question is of the fact that in going from the first form to the second form, did we pick up any new solutions, lose any solutions? And so we're phrasing that question as, look, comparing the solution sets of the first equation and the second equation. And I'm trying to make concrete what the meaning of that is. We'd like to know, when is this true? Or we hope that this is true between here and here, because that means Gauss's method is safe. And I've said two sets being equal. Here's what I mean by the solution set of S1. Here's what I mean by the solution set of S2. What I mean by them being equal is that they have the same elements, and having the same elements is equivalent to these two implications. And what I've tried to explain is what this notation, say S2 equals this, means is this property here is the defining property, logical property of the set, which is the test that tells you whether an element is a member or not a member or not a member. And so I use it by, say, taking a candidate set of numbers, say S1 and S2, and plugging in the values, the numbers for the variables, and seeing, is this equation true or not? Because if I choose two numbers and I put them in here and it makes it true, that means this is a solution. And if I choose two numbers and put them in for this equation, it's a solution. And if I then say, well, what does this S member of S1, S member of S2 mean? What they mean is these equalities here. So this final logical equivalence, which we'd like to know, is this true or not? If this is true, then the solution sets are the same because the defining properties of the two sets are the same. That is the take-home message of this little talk, so to speak. That and you can see that, in fact, if this is true, if the left-hand side is true, all I have to do is, that this is just a special case of something you've done all the time. I mean, you'll say, if I have x equals y, well, if you just have some numbers like x equals y, well, you know that implies that 5x equals 5y. That doesn't change. That's not going to change anything. And I can go back the other way, because this 5 is not 0. I just have to divide by 5 to go back this way. And similarly here, this is just a number here and a number here, and this is a number and this is a number. So let me maybe make this more like this. If I have two numbers, R and S, but I know that I don't know, I have them as, say, names, like I have a number R and well, let me not use S. I have a number T here. I say, well, if R is equal to T, then I know for sure that K times R is equal to K times T. And if I knew that K times R is K times T, I can divide by K, because K is not 0, and get back, if this is true, this has to be true. And if the right-hand side is true, the left-hand side is true. So this is just a case of numbers. This is just elementary arithmetic. And so, but that's what it boils down to, is just that if I have two numbers that are equal, I can multiply both sides by a number, and I get something that's true. And if I have go the other way, I also have something that's true. So this is sort of the whole take-home message of that the core of the idea, asking does this equation have the same solutions as this one, is just the statement that the plugged in values of one equation have to apply the other equation. Now it's all dressed up with letters here, so it's hard to look at. And the reason we need the letters is because we need to ensure that Gauss's method works with all equations, not just with particular ones. And I haven't done this with Gauss's method here, but so this is sort of on the way there. So what do you guys think? Okay, so I can still record, but what I want to do is I want to chop this up into